People have been arguing for centuries that 0.9 recurring can't equal 1. This might be because we can produce a pretty good argument against any proof that 0.9 recurring equals 1. And we will examine one of those arguments now. Mathematicians will tell us that if we accept 0.9 recurring is a real number, then we have to accept that it does equal 1. But this symbol 0.9 recurring was around for over 200 years before real numbers were defined to be limits. And this timeline shows a period of over 200 years where unending decimals or real numbers were not defined as limits. And if we take 0.9 recurring to represent the unending series 9/10ths plus 9/100ths and so on, then we can call it an old timer, because unending series have been around for thousands of years. Long before the new kid on the block called real numbers as limits came along. Perhaps the main issue with the limit approach is the question of whether or not it makes sense to define the sum of an unending series of non-zero terms to be equal to a constant value. This idea that unending non-zero terms can somehow equal a constant is often justified by the concept of converging to or tending towards. We might think of the series in terms of a number of jumps, where each term in the series is produced by a looping algorithm. So the first jump needs to get us 9/10ths of the way from 0 to 1. The next jump only gets us a further 9/100ths, and the third jump advances us by the tiny distance of 9,000ths. We appear to be approaching the value 1, but there is a type of approaching where you will eventually reach your destination, and there's a type of approaching where you won't, and this is the latter. A geometric series is a series with a first term a and a common ratio r, where r is what you need to multiply the first term by to get the second term. And so for 0.9 recurring, a is 9/10ths and r is 1/10. We can form an expression for the sum to the nth term that simplifies to k minus k times r to the power n, where k is a divided by 1 minus r. We could describe k as the constant part of the expression, and minus k times r to the power n as being the variable part of the expression, because this will vary as the value of n varies. So, for a so-called absolutely convergent series, the constant part a over 1 minus r is called the limit. So, the sum is defined to be equal to the limit. If the expression a over 1 minus r was really the sum of infinitely many terms in a geometric series, then 1 plus 2 plus 4 plus 8 and so on would sum to minus 1. And minus 1, minus 2, minus 4, minus 8 and so on would sum to plus 1. But supporters of real numbers wanted to claim that the expression could be said to equal the infinite sum in some cases, and so they used definitions, notably convergent and divergent, to exclude the cases that appear to lead to absurdity. If you're not a mathematician, then you might be surprised to hear that definitions or axioms don't need to be valid, because they are deemed to be true by definition. And so if I want to prove that my chair can fly, I could declare that, by definition, all men can fly. And also by definition, my chair is a man. It then follows that my chair can fly. Obviously here, I have defined my way to the answer that I want to achieve. In the same way, proofs that rely on the formula for the sum of a geometric series are proof by definition rather than proof through deductive reasoning. Finally, thank you for taking the time to watch, and I hope you enjoy my other videos.